The second part was asking whether the same intersection event, give an example in which the same intersection event is detected twice. Okay, so some of you did not understand the question very well and thought whether interpreted it like whether two line segments can intersect at 2 points. The question was not asking this, okay? It's just the same intersection event, meaning that it's a single intersection point. A single intersection. All you need to do is ask about a case in which the same two line segments become neighbors, then become non-neighbors, and become neighbors again. So if they become neighbors in 2 different times, what we will do is, if they intersect, you'll be detecting that intersection twice. And one easy example is this. So they're intersecting. And imagine there's a line segment right here. So this intersection I, and this is my sweep line going downwards. At this point, at this event point 1, which is the end point of this, let me name it segment 2 and segment 1. So at the upper end point of segment 2, these two are going to be neighbors, S1 and S2, and we are going to detect this intersection I and put it in our event queue. And at this event point, and at this event point, this one is going to be, S3 is going to be neighbors with S2, and when S3 is neighbors of S2, no events are detected, new events are detected because they don't intersect. I mean, some of you thought that when two segments are neighbors, we always have an event for them. No. When two segments become neighbors, we just check whether they intersect or not. If they do not intersect, no new event is generated. Only when they intersect, we generate a new event and put it in the event queue. So at this point, S3 becomes neighbors with these two, and we don't detect an intersection. And at the lower end point of S3, when we remove S3 from our study structure, S1 and S2 become neighbors again, in which they are tested again for intersection. And we find again the intersection point I, so the same intersection point is detected twice. Okay, so an example like this was being asked in the second part of the question. So, any questions? Any comments? So I hope it's clear. Okay, so let's continue with the map overlay problem. Let me erase this part first. So let's recap. Let's try to remember what doubly connected edge list was. In doubly connected edge list, we had records for vertices, edges, actual half edges, and faces. Okay, so we have to represent a subdivision of the plane. We use this representation of with records, vertices, edges, and faces. And last week, we didn't actually solve this exercise, but if you remember the vertex records, a vertex, even if it has, it may have, what it may happen is that, so this is one half edge like this, that goes like this, and this may be another. There may be the same vertex, V1 for example, may be incident to two different faces. Okay, so the same vertex V, and if you remember the vertex record, I mean it's the origin. For example, this is E11, this is for example E22. Okay, these two half edges. The one that is going this way is E22. The one, so this is E21, and this one the counterclockwise traversal of this one gives phase 1, and the counterclockwise traversal of these edges gives phase 2. Now, as you can see, V1 is the origin of two half edges, both E11 and E22. But in our vertex records, we only store an arbitrary edge, which for which this vertex is in origin of. Okay, you remember in the example there was this V1, and it was actually again it was something like this. It was incident to more. It was the origin of more than two edges, but in the vertex record we stored only one such one of these edges in which the vertex is origin of. Okay, so the question is, I mean, this small exercise, is this enough? I mean, just with just one, for example, if I in my vertex 1 record incident edge is E11. Okay, so how are you going to find out E22? Okay, V1 is also origin of E22. So can you give me an algorithm to find, and in extreme cases there may be many other half edges as well. Maybe let's name it as E33. This may be another phase. Okay, there may be another phase. So there may be like E11, E22, and no, we don't have E33. Let's name it E32. So it's 1 and 2 are used for the twin edges. So we have two twin edges. We don't have the triplets of edges. So can you find E11, E22, and E32 given just that the E1 for vertex V1? So that this is the exercise that the book was asking. Is it possible to find all these edges if I'm just given E11? Well, so E11 has no priority over E22. I could have just given E22 as well. But can you find all the vertices, all the edges around vertex? And this, not all the edges, only the edges in which V1 is the origin. For example, in some of these edges, the twin of these edges, V1 is the destination. Okay, so the twin of E11, which is E12, here, so this is E12. V1 is the destination of that half edge, and we don't store destinations; we just store origins. So, does anybody have any idea about how we can find whether this is enough, or we should actually have all of them listed like this? So should we list all the edges, or is really one of them enough? Can we find all the others if one of them is given?
Next previous.
Yes, next we can. The edge records have next previous records. So by using them, maybe we can find it. So how? For example, what is E22 here? If you look at E22, so it is E11, so E11 was this one. So E22 is actually the E11 twins next, right? So, by using this, by, for example, going each time, take the twin of this edge, take the next of it, and you find E22. Now, what is the twin of E22? It's E21. E21's next is E11, so we found E11 again. So it seems like we're stuck in a cycle. Like, will we be able to ever find E32? So this way, maybe I have written the half edges incorrect. Maybe we will never be stuck in a cycle. Maybe if you go this way, taking the next of the twin of that half edge, maybe you'll have a way to traverse all the vertices, or all the edges around this vertex in a certain counterclockwise or clockwise order. So is it possible to visit all of them? This is my question. So let's see in this example, let me draw it in a more clearly. The goal is to find out all the edges in which V1 is their origin. Okay, so that's the problem. So, I mean, if we can also, I mean, if you find the edges, it means that you find the faces, because the edge record also has the incident face record. So finding the edge means that you each half edge has a unique bounding face. I mean, it bounds, each half edge bounds a unique face. Okay, so this is the incident face of that half edge, and it is put in that record. So let's see if I did anything incorrect. So I have this face, which is, oh, okay, so that's the incorrect thing. So this is the counter, this should be, this face is not, let's see, it's clockwise, so it's a hole. So let me try to, okay, actually this one is clockwise as well. The only thing that, yeah. Yeah, this one is also clockwise. So these are all holes actually. These do not indicate these faces. If these edges are going to be the outer boundary of F2, actually what I have drawn here is the whole of this face that is here. Okay, so if I have F3 here, this cycle that I have drawn here belongs to F3. It's a whole of F3. Because don't remember, we have our main convention here is that, I mean, we just chose to do that. Any half edge, the incident face is lying to its left. Okay, whether it's an outer boundary or whether it's an inner hole, if the unique bounding face, I mean the unique face of that edge, half edge, always lies to its left. So if I have this cycle, this boundary cycle, its face is here. Okay, so its left is here, so it's going to be bounding that face. Now, so let's have a correct representation now for these. Now I'm going to draw the outer boundaries of these faces. Let's have this V1 again. Okay, so let's have a counter clockwise traversal this time. Okay. Now, this boundary cycle is going to be bounding the outer boundary of this face. So if this is my F1, what I have drawn here, this by going over all these next records of these half edges, you complete this cycle and it becomes a boundary cycle, and it becomes the outer boundary of this F1. And the twin records of these edges these are the twins of these edges, are going to be bounding this face F3, which is the unbounded face at the end, from the which doesn't have any outer boundary. Okay, now let's imagine V1 also has another two other incident faces. So let's have V1 as the origin of another face like this. Okay, in counterclockwise order, this is F2. And the twin records of these ones actually this one becomes, now the pink and white, the outer inner boundary switches here. So again, this becomes whole. It's the inner boundary for F3 as well. And let's have another phase, for which V1 is the origin. Okay, let's have it, for example, this way. So V1 is also origin of, so, okay, yeah, actually we have that. So this pink one is the half edge in which V1 is origin, okay? So V1 is the origin of this pink half edge. And let's have a counterclockwise traversal of that, like this. And let's name it F4, for example. Now, let's name these edges once more. So let's name this pink one as E32. And this one E11. And this one as E21. So these are the, yeah, let's name it. So it's maybe sometimes impossible to say all the inward edges is going to be indexed by 1. I mean, last time we were talking about a convention in which all the inner boundaries, let's name the half edges, let's index them 1 and the outer vice versa. But sometimes it may not be possible. The same half edge may be an outer boundary for this, but inner boundary for this. So this naming convention may not be possible. But these are the, so everybody agrees I didn't do anything wrong, right? These E31, E11, and E21 are the three vertices in which, three edges for which V1 is the origin, okay? Now, given one of these, E11 for example, will you be able to find E31 and E21? So let's use the idea that we have come up. So the next of their twin half edges. So E11, the next of E11, the twin of E11 is this pink half edge. Its next is E21. So we have found E21. And the twin of E21 is this. And its next is E31. So we have, so it's like we are doing clockwise traversal. If we do that by starting from one of these edges, we are doing a so let's do the same thing for E31. The twin of E31 is this one. Its next is E11. So if we continue this, so given this incident edge, if we do something like this, the twin of incident edge and its next. Okay? If you do this in a loop, you are going to traverse all the edges around V1 in clockwise order. So it is possible, but I mean, we haven't proved this. We have just shown this on an example. So the next thing actually should be to prove that it works for every such vertices.
Hocam biz burada bütün edge'leri traverse ettik ama şunu diyebildik mi? Bu edge orijini V1'dır, bu edge'in değildir. Biz sadece next yani traverse ediyoruz ama bir bilinç yok yani.
No, actually, no. What we are doing is each of these during these traversals, each of what we get at the end of this operation is always an edge for which V1 is the origin.
Always.
Yes. Okay, so but we need to, I mean, it's like we need to prove this. Can you, maybe actually it will be a better homework for you to prove this. I mean, it may not be very difficult, okay? It's probably going to be very easy. Again, you can prove it probably by induction. I mean, just if you introduce another vertex, whether you'll be able to find it or not, I mean, you'll be able to do it. So let's try to prove this for next week as your homework, okay? I'm going to write this question and post it on the website tonight. So prove that this next twin incident edge idea to go to traverse all the edges around V, for which V1 is the origin. All you need to do is this in a loop, and this is going to provide you a clockwise traversal of the edges. Okay, so this was a recap. I mean, we remembered what the half-edge records, the vertices, faces were. Okay, now let's come to our problem today, which is given two different subdivisions of the plane. They may indicate, one of them, for example, may indicate the forest regions in Turkey. The other may indicate the weather pattern, for example, the humidity regions of Turkey. And we may want to see whether this forest and humidity is related, correlated or not. Okay, so these are two different subdivisions, and overlaying these two subdivisions on top of each other, we are going to generate another subdivision, which is, we don't say it's the intersection, because we combine both of them into a richer, which probably contains more faces. The number of faces it contains is going to be more, and I just want to demonstrate it on a simple example, what we mean by overlay. Okay, now I'm going to draw you two subdivisions, which are very simple. Okay, one subdivision is this. I have F4, F1, F2, F3, and these are my vertices. And these edges are the outer boundary of F1. Their half edges are going to be, this half edge is going to be the outer boundary for F2. So, I mean, drawing these half edges really complicates the graph a lot, but so just this, imagine all the half edges exist there, okay? Now, this is one subdivision. Now I'm going to draw another subdivision, which exactly has the same vertices. So this V1, V2, and also, the corners are going to be shared, V3, V4. So this V6, V7. Okay, it's some arbitrary order. So I'm going to show you another subdivision in which V1, V2, and V6, V7 are shared, but we have some additional vertices like that. So I'm drawing in a separate place, but just indicating that these are V1, V2, V7, and V6. They have the same coordinates, okay? So I'm just showing a different subdivision in a different place, but they are actually, when you are going to overlay them on top of each other, meaning that we are going to put this on top of this thing, and we are going to create a new subdivision. And this one has these vertices, which are different coordinates from these V3, V8. Okay, so the overlay problem is, so this has a doubly connected edge list to represent this subdivision. This has a different doubly connected edge list to represent this subdivision. The overlay of subdivisions is to put these two doubly connected edge lists on top of each other. And so this is V9, V10, V11, V12, and find the vertices create a doubly connected edge list, a single doubly connected edge list for this subdivision, which has now 10 faces. Each of them, this had 4 faces. This one has also 4 faces, the initial subdivision, but this one has 10 faces. It's not like the total number of faces is not the summation of the. So this example shows that when you overlay 2 subdivisions, actually the number of faces you are going to get can be more than the summation of the number of faces each individual subdivision contains. So this is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 faces. So the goal is to create vertex, edge, and face records for this new combined subdivision. Okay, so this is the map overlay problem. This is not an easy thing to do. I mean, the algorithm is actually very complicated because it's what we do is we try to first observe whether we can use any existing records from the from the individual subdivisions. Right? Each subdivision has their own doubly connected edge list. Can we reuse some components? For example, if there's an edge record here, can we reuse this edge record? Actually, can we reuse this edge record in this new subdivision? For example, look at this edge here, or look at these 2 half edges here. Are they affected by this overlay? I mean, these 2 half edges, which were in the white subdivision, which had, let's name these subdivisions. I refer to them a lot, so I need to, let's name these. The white one is the vertical subdivision, and this is the horizontal subdivision, and the combined subdivision, I'm going to name it as the combined subdivision or overlaid subdivision. Okay, I'm going to name it as combined. The vertical subdivision is the first subdivision I showed here, and this is the horizontal subdivision. Now, if you look at the edge records of the vertical subdivision, look at these edge records. The same edge records exist in the combined subdivision as well, right? So this observation shows that maybe we can reuse when we are building this doubly connected edges of the combined subdivision. We can reuse some records. And which records we can use, which records we cannot use. For example, we also introduce some, for example, at these points, in order to have these as separate faces, we need to introduce some new vertices here, right? For example, V13, V14. So new vertices are going to be introduced in the combined subdivision. But an important observation is that these new vertices, and also when we introduce this new vertex, it means that we need to modify the half edge record that connects V5 to V8. So this half edge record that combines V5 and V8 is divided into 3 regions, 3 half edges at these intersection points. So I cannot reuse this whole half edge. This whole half edge does not exist anymore. There are vertices on the way to V5. So I cannot, what we observe is that the only half edge records that we cannot completely reuse are the half edge records which are in an intersection, okay, which intersect with half edges of the other subdivision. So therefore, the line segment intersection, this is related to the line segment intersection problem. So we can compute the overlay by using a plane sweep and detecting these intersections, and at these intersection points doing certain things so that we have the correct vertex and edge records of the new combined subdivision. Okay, so we are going to extend the line segment intersection algorithm to compute this. And finding the face records, I mean, the new face records are going to be much more difficult than just the vertex and edge records. So the algorithm handles these two things separately. First, it makes sure that the vertex and edge records of the combined subdivision is correct. After it finds those vertex and edge records, it traverses these edges, for example, to find boundary cycles, then assign these boundary cycles to faces. Okay, so the finding of the faces of the new subdivision is done in a separate phase after edge and vertex records are handled. So I'm going to therefore describe the algorithm in two separate phases. And actually, it also comes with the last third phase, in which after we found the faces, we may need to, what we want to do is, if the individual doubly connected edgeless, the vertical and horizontal edgeless, if the original faces were containing some attributes, for example, saying that the humidity in this vertical stripe is this, and the forest density in this horizontal stripe is this. If they had some attribute information, we want to carry these attribute information over here. So what we want to also find out is that, for example, this region contains F3 from the vertical subdivision, and let's name it, for example, FA, FB, FC, and it contains, for example, FB from the horizontal subdivision. So when we are finding these new face records, we need to also find out which face of the individual subdivisions they are coming from to say that, okay, this is the region with this humidity and with this forest density, to have the attributes. And this is done as the third phase to find, because sometimes what happens is that even though you don't have an intersection, I mean, a certain face here originally may be the face of only one subdivision. I mean, imagine this was not intersected by anybody, but a subdivision of the other pink subdivision was actually containing this. So in that case, it becomes difficult to say that this is also F3 and FB if there's no intersection at all. So how are you going to find each face here is going to be because all of them, this provides a subdivision of the whole plane, and this provides a subdivision of the whole plane as well. So there is no region here which is only consisting of a single individual face. Both of any face here you choose is going to contain both attribute information from both individual subdivisions. Okay, so because both of them span the whole space. So the faces here you have span the whole space. The subdivision here span the whole space, whole plane as well. So you are going to propagate this face information in the last final step. And the book actually does not describe an algorithm for this. It leaves this part as an exercise, the third part. And actually the solution is, again, looking at neighboring line segments during plane sweep. Looking at the neighboring line segment, neighboring half edges actually. You can use their incident face records to compute this in the last phase. So let's start with the first phase. What happens, how do we find the vertex and edge records of this overlay combined subdivision? If there's an intersection between the segments from the same subdivision, from the vertical or horizontal, such intersections only occur. That's also another assumption. For a single subdivision, we assume that these edges in a subdivision itself do not intersect in a single subdivision if we have such an intersection, what we do is this is our vertex, okay? We have half edge records individually here. So what happens is that this becomes our line segment. So the half edge records within a single subdivision actually do not intersect themselves in the middle. Okay, if they were intersecting, we can pre-process this to get rid of these, to turn these intersections to vertices. They become the vertices of this subdivision. So the only, what happens is that in a single subdivision, these line segments only share endpoints. Okay, they only share endpoints. And if you consider these endpoints, if you consider this point as an intersection during the plane sweep of this, what happens is that you see that it's already, you don't need to do anything in the plane sweep. You don't need to do anything if segments from the same division intersect at that point. The only place where you need to update the overlaid subdivision is that when segments from two different subdivisions intersect. So the only place, the only action that we are going to do during this plane sweep is when we detect, for example, this half edge intersects with this half edge. What we are at this intersection, what do we need to do? What we need to introduce a vertex, for example. We need to divide these half edge into two half edges. So from two half edges here, we are going to at the end have 4 half edges. So what do we need to do at these intersections between two subdivisions is the main problem. And the book describes a difficult case, like a degenerate case, to show how this can be done. And I'm going to show you that example to describe how we are going to rearrange everything around the intersection point. So now I'm going to forget about this example and follow book's examples on this topic. So the example is this. The intersection occurs at a vertex of one of the subdivisions. So, and that vertex may be incident to many edges. So this is one of the subdivisions, and this is my vertex V. Okay, I just show the edges as full edges, but each of them actually is composed of 2 half edges. And in this case, the book describes we have a half edge from the other subdivision like this. It intersects, the pink subdivision intersects the white subdivision half edges at this common intersection, at this vertex V. Okay, so what do we need to do? So before the overlay, we had a single half edge record here, a single half edge records here. So what do we need to do to convert this? So after the map overlay is done, what we have to do is something like this. The correct subdivision after this, handling this intersection is going to look like this. So we have vertices and this one. Okay, so I need to have this many half edges around this vertex V. So this is a single vertex V here. Okay, and so there are, in order to do that, we need to change the previous and next records of many vertices around this V. Okay, in order to have this valid half edges around V, first the first thing we need to do is we need to divide this single half edge. Let's use the same terminology. Let's say this is E, okay, and pink one is subdivision 1. Okay, so what we need to do is we need to replace the single half edge E by two half edges, E prime and E double prime first. We need to divide it by 2, and we need to also set its half edge records accordingly. And the half edges is going to become 4 half edges at the end. At the end, we are going to create 4 half edges here. Now, after adding these new half edges, so we need to introduce our half edge table. Our edge records table is going to, we are going to add 2 new records, which are going to, after dividing this existing record into 2, we are going to be adding 1 new addition for, this E is going to be divided into 2 records, E1 and E double prime, and we also need to add half edge records for their twins. So twin E prime and twin E double prime has also need to be inserted into this list, and we need to, if you remember the half edge records, we need to set their previous and next records, and maybe we also need to update their origin records as well. Okay, not all of them has origin V. Some of them has their origin. The destination of this is origin of the coming half edge. And after handling this pink, after dividing this pink into 2, we also need to do something else. We need to update these neighboring half edges. Their next pointers also have to be updated. Okay, in this one, for example, its next record, the next record of this one, if we are doing a counterclockwise traversal here, the next of this half edge that was going this way was this. Okay, this was its next. Now its next has to be this. So the next and previous pointers of these neighboring edges also have to be updated. So the tricky part becomes, what are the neighbors of these edges? And actually, if you remember the neighboring information, we were using the same thing in line segment intersection, right? When we checked the event points, new intersection point, this was what we were doing. For a given line segment, its neighbors to the left and right are stored on the study structure. So actually, we can access these half edge records by using the same technique in line segment intersection. So therefore, all these pointers have to be updated considering these situations. The neighboring edges have to be updated. And at the end, we are going to, at these intersection points, we are going to update the half edge records around it, update their previous next records, and this process, and we are going to do this in a plane sweep. We are going to detect these intersections in a plane sweep, and we see that these record updates actually is on the order of the degree of this vertex V, the number of neighbors. It's not going to be, it's not going to, the main thing is not going to increase the complexity of the overall plane sweep. At each, handling each intersection, we need to do steps that is on the order of these vertices, and in total, the number of it's not going to be it's going to be linear in terms of the entities in our doubly connected edge list. So it's not going to change the complexity of the subdivision. So we can still do n log n plus k log n time complexity, where k is now the complexity of the subdivision. Okay, the overlaid the final subdivision, how many faces plus edges plus vertices it contains. So again, it's an output sensitive algorithm, because if the two subdivisions intersect at many points, it means that we are going to have that many vertices and that many faces And for planar graphs, the Euler formula relates the number of faces with number of vertices and edges, but it is linear. So the final complexity is going to be the same as the line segment intersection problem. Now, after we have these correct vertex and edge records, the remaining thing is, how are we going to find faces? Okay, and for example, a face may have multiple holes and multiple inner boundaries, a single outer boundary. After we have all these records, how are we going to find faces? This is our next question. By going, first of all, what we are going to do is, by going over each edge record, for example, by starting from this edge record and traversing its next pointers and until coming to the same edge record, we can detect boundary cycles. Okay, all boundary cycles, after we have our vertex and edge records, all boundary cycles can be detected. And the boundary cycles actually, if it's a hole, okay, a hole of a face is actually an outer boundary of another face, okay? So if you detect the number of boundary cycles, the number of faces in your subdivision is equal to the number of boundary cycles plus 1, and this one is for the unbounded face, okay? The unbounded face is not going to have a boundary cycle for it, and therefore if you detect the boundary cycles, the total number of faces are going to be the number of boundary cycles plus 1. Now, the thing becomes, how are you going to find out which boundary cycle is a hole, which boundary cycle is not a hole? Now, we know that, I mean, by looking at if I give you a boundary cycle, you'll immediately, I mean, as soon as you see it, you can see, okay, this is a counterclockwise traversal, this is a clockwise traversal. You can understand whether it's an outer boundary or an inner boundary, right? Now, let me try to, I'm going to show you that the detection of, by starting from an edge, for example. Is this a counterclockwise or clockwise traversal? It can be both, right? What about this? Is this a clockwise or counterclockwise traversal? Any questions? How many say it's clockwise? Counterclockwise? Okay, so you're smart. Well, all of you are smart. It can still be both. Okay, I mean, until you see the whole face, you can never be sure that it's counterclockwise. I mean, it seems like it's like a trick. It seems like a clockwise traversal, but what if I do this? Okay, now it became a counterclockwise traversal. Okay, so this one becomes the outer boundary of something, but this one becomes the inner boundary of the whole for this face. This one becomes. Now, the trick to find whether given a cycle, if you know the cycle, okay, if you know the whole cycle, okay, this is the whole boundary cycle, you can see now it's a counterclockwise traversal, so it's an outer boundary, okay? But how can you program this? So how can you put this rule? If I give you these edges, how are you going to know, how can you detect it's a counterclockwise traversal or clockwise traversal? I mean, it's so intuitive to us that you may even not understand the problem yet, because as soon as you see, okay, it's counter. What's the difficult thing about this? But if I tell you to write the code for this, detect. If I'm going to give you some edges, I know that there are cycles. So find out that it's a boundary or it's clockwise or counterclockwise traversal. So how would you find that?
Geri en son döndüğümüz noktanın edge'in sağındaki nokta mı yoksa son yani hani şu şekilde dersek döndüğümüz nokta edge'in solundaki nokta olur.
I have to get this. I think Ömer Hoca is calling. Alo. Merhaba Ömer Hoca. Tamam. Ben de şimdi dersteydim. Dersten çıkıp geliyorum yanınıza. Binanın kapısına geliyorum. Bitiyor ders. Tamam, tamam. Görüşürüz, görüşürüz. Okay. So, I mean, that's the idea actually. We are going to look at the leftmost vertex of this cycle. The leftmost vertex can be detected. Okay, we can detect the leftmost vertex. If there are two, if they have the same x coordinate, we can choose the lower one. And the angle it makes with its next should be less than, if we are going to, for example, we are going to look at this, and we are going to look at these two edges. And this angle is going to tell us whether it's counterclockwise or clockwise traversal. Okay? But it's the same idea, to the left or right. I'm looking at the angle, and the same thing is the same. So this is, we are going to detect like this. So after detecting all the boundary cycles, we are going to generate a graph. And this graph is going to have a node for all boundary cycles. Any boundary cycle detected is going to have a node in this graph. And we are going to put an arc between nodes in the graph if there's a whole boundary cycle, and if we find another boundary, it may be inner boundary or outer boundary, so it may be a clockwise or counterclockwise traversal boundary cycle here. We are going to put an arc between this boundary cycle and to the first cycle that is to the left of it. So the holes are going to be linked together, and at the end, the final hole is going to be linked to its outer boundary. So after we create this graph is going to have lots of disconnected components and connected components. And each connected component is going to give us the incident, the inner components of a face and a single outer component of the face. So this is going to be done by processing this graph. So the second phase of the algorithm is done like this. You can set the edge records, the face records of these boundary cycles. You can set whether it's an inner boundary or outer boundary. And the last phase is going to be determining whether which phase is containing which other phases of the individual boundaries. Okay, so this concludes our chapter 2, okay, map overlay. And I'm going to, next week in the beginning of the lecture, I'm going to go over this graph idea once more to make it more clear. And for your homework for next week is to show that this twin, next twin edge is going to give us a traversal of the incident edges of a vertex. Okay, prove that this works. This gives a clockwise traversal of the edges around the vertex all the time. Or provide a counterexample that it does not. Okay.